Welcome to this video on geotechnical engineering, where you'll be given a chance to refresh your knowledge on geotechnical engineering. The video contains basic knowledge about soil, means we're going to discuss types of soil, soil parameters, stress, and also safety factors in relation to soil and geotechnical engineering. Let's begin with types of soil. If you're a geologist or geotechnical engineer, you use the same terms for different types of soil. However, there's a slight difference in grain size definition for some types of soils. However, as geotechnical engineers, we'll be using the scale to the left. This definition was taken from the Danish Geotechnical Society Bulletin 1E. In the Geotechnical Bulletin 1E, I also found this example of 4 grain size distribution curves. I have a curve for clay till, more commonly known as moraine clay. Also an example of clay of high plasticity, and 2 types of meltwater sand. I suggest you press pause on the video now and then see if you can determine which curve belongs to which type of soil. The long line you see here is clay till with a clay content of just under 20%. The clay of high plasticity is the curve you see up here. It has a clay content of approximately 75%. You'll also note that this specimen has no sand particles, so it only consists of clay and silt. You then have type of sand here. You can see with a very big content of fine sand. Have another sand sample which is more coarse, a lot of high content of coarse sand and even fine gravel. If you're interested in knowing more about geotechnical engineering, I encourage you to join the Danish Geotechnical Society, or you can see the website here, Dansk Geoteknisk Forening.dk. It's a free membership for students, and throughout the year there are interesting meetings about geotechnical issues. Also, you have online free access to historic geotechnical literature. So to summarize which types of soils we normally work with in Denmark, we have cohesion soil, the fine particles, friction soils, silt, which can act both as a friction soil but also as a cohesion soil. Organic soils, have different types of those, and also the man-made soils, which we more commonly call fill. Rock is not very common in Denmark. Bornholm has bedrock, but other than that you can sometimes find limestone in Copenhagen, but it's not very often that we work with rock either. When we work with soil as geotechnical engineers, we make use of soil parameters that allow us to perform calculations. I'm going to look at some of these parameters relevant for earth pressure. Friction angle is a very important parameter for soil. If you want to understand what is a friction angle or angle of shearing resistance, you have to think of a pile of soil on the ground. The steepness of the pile, you can translate that into the friction angle. Another parameter that we work with is cohesion. In cohesion we have short-term state, or as an undrained state. Sometimes it's stable, but we also work with a long-term state. Sometimes we call that a drained state, where the soil changes character and has different strength parameters. So with clay, it's important that we investigate both the short-term and the long-term state. The friction angle, or the angle of shearing resistance, use the Greek letter phi. Sometimes we write the PL for plane. Sometimes we write TR, that's for the triaxial. So if you've tested the soil in the laboratory and they found the triaxial friction angle, you can write phi TR. Sand, the phi prime is the effective friction angle, can be determined as 1.1 times the triaxial friction angle found in the laboratory. And the K is then the characteristic value. For clay, we either have a friction angle of 0, which is the case in the short-term state, in the undrained state, or the friction angle characteristic value is the same as the triaxial value. That's the case in the long-term investigation of clay. Also, if you do laboratory tests, the inclination of the tangents is the same as the friction angle. Cohesion soils, said before, we have an undrained or short-term state that we use the value Cu, the undrained shear strength. The unit is kilonewton per square meter or kilopascal. In the drained state or in the long-term state, we use the effective cohesion C prime. So the unit is the same, kilonewton per square meter or kilopascal is the same. Let's stay with cohesion. If you want to determine the undrained shear strength, it's typical that you perform a shear vane test, because CV, which is the result of the shear vane test, is often equal to Cu, the undrained shear strength. Can also, if you have fractured clay, you reduce the undrained shear strength to only a third of the tested value from the shear vane test. Cohesion soils, the effective cohesion, or C prime, often is calculated as 10% of the undrained shear strength. However, it's never more than 20 kilonewton per square meter. Have this C prime for over-consolidated soils, and also in cases where you have loading, meaning that in a passive earth pressure. C prime is also very often just determined to be 0. That's for normal consolidated soils, or in doing situations where you're unloading the soil. During the semester, we'll talk more about when you can determine C prime as 0, or when it's okay to use C prime's actual value. So an overview of the terms used so far. We distinguish between cohesion and friction soils, and then also we have an undrained state, or the short-term state, versus the drained or the long-term state. If we take the short-term, the undrained first, you use for cohesion soils, you use the undrained shear strength Cu. You assume the friction angle to be 0. In friction soil, it's not relevant to talk about an undrained state, because friction soil is always in a drained state. So let's go to drained state for cohesion soils. We use the term C prime, or effective cohesion, and we also use the term the effective angle, friction angle, which is not 0. Friction soil, we use the friction angle, and there's no cohesion in friction soil. You might be thinking, Well, you have short-term and long-term. How many days does it take for the soil to become drained, meaning that you go from the undrained to the drained situation? Well, that's actually a very good question. It could take a few hours, a few days, or a few weeks. I don't have the answer in this presentation, but it's worth thinking about that. It doesn't necessarily happen instantaneously. You can find additional information on soil parameters in special literature, for example, handbooks. In Denmark, we often use the Teknisk Stabi, which has typical values for different types of soils, empirical factors, and also rules of thumb. Now on to stress, which is very much related to earth pressure, which is a big part of the fourth semester course. So let's talk a little bit about stress. The textbook, chapter 2, has some definitions about stress. When there's no flowing groundwater, meaning that the groundwater is still standing. We talk about the total stress, the pore water stress, and the effective stress. This should be known by you, but we have some example on the next few slides. One example, we are to calculate the total stress. If you have some soil with some groundwater in it, let's say that the soil is sand with a dry weight of 18 kilonewton per cubic meter. Gamma D is the dry weight. It has a saturated weight of 20 kilonewton per cubic meter. Call that gamma M. The surface level is in plus 12. Let's say the groundwater table is in plus 10. And the bottom of our sample is in elevation plus 3. So let's try to calculate the total stress at surface level plus 12 and at the groundwater level and at an elevation of plus 3. And determine that we have a distance from surface level to the groundwater table of 2 meters. And then we have a distance of 7 meters from the groundwater table down to plus 3. So if we take elevation in level plus 12, the stress is 0. In level plus 10, we calculate the stress by taking the density of the soil and multiplying it with the depth d1. So the stress is 18 kilonewton per cubic meter multiplied by 2 meters, giving us a stress of 36 kilonewton per square meter. In the elevation plus 3, we calculate the stress by taking the density of the soil above the groundwater multiplied by the distance d1. And then we add the saturated weight, gamma m, with the distance d2. So now we have 18 multiplied by 2 plus 20 multiplied by 7, giving us a total stress at elevation plus 3 of 176 kilonewton per square meter. If we were to draw the stress as a figure, it would look somewhat like this. We have the same example, but this time we do not want to calculate the total stress. We just did that. Instead, we want to calculate the pore water pressure or the pore water stress. We take the same 3 elevations and investigate the pore water pressure. In elevation plus 12, the pore water stress is 0. In plus 10, it is also just 0 because this is where the groundwater table starts. At elevation plus 3, we are at a depth of 7 meters below groundwater table, so we calculate the pore water stress by taking the density of water, multiplying it with distance d2. Normally we assume density of water to be 10 kilonewton per cubic meter. So the pore water stress U is 70 kilonewton per square meter in this depth. Again, we could draw the stress as a triangle. So for the same example, let's try to calculate the effective stress. The same 3 elevations, plus 12, plus 10, and plus 3. At elevation plus 12, the effective stress, sigma prime, is 0. 2 meters down, the same calculation as we have before. So the total and the effective stress is the same, and there's no groundwater. 36 kilonewton per square meter. 7 meters further down at elevation plus 3, the effective stress is the stress of from the first 2 meters, the dry density multiplied by depth d1, but then you add the effective weight or the saturated weight minus the weight of water that you multiply then with the depth d2, giving you an effective stress level of 106 kilonewton per square meter. If you were to draw this stress as a function of depth, you would have a figure looking somewhat like this. So to summarize the results that we have so far in the 3 depths, we have the total stress, the pore water stress, and the effective stress, or 3 depth listed in this table. If we take the graphs we have, the total stress was the black triangle. Also had the blue triangle for the pore water stress, and the effective stress of this last figure. If we rewrite the term for how to calculate the effective stress, we could say that the total stress minus the pore water stress equals the effective stress. And I think if we look at our figures, we prove that it's right. It's very important that you understand how to calculate the stress with or without the presence of groundwater, as this will be very important in the semester when we calculate earth pressure. Finally, I have a few things about safety factors and the Eurocode 7, and also the Danish National Annex, which is the annex that we use here in Denmark for interpreting the European Eurocode 7 document. They are quite similar, but of course the Danish National Annex introduces some changes to the Eurocode 7. Examples are the use of consequence class CC, and also something called a consequence factor, KFI. We'll get back to those. The consequence class is a product of the Eurocode 0. We have CC1 for simple structures. However, they're not relevant for geotechnical structures. So in geotechnical engineering, we are only working with CC2, normal structures, or CC3, critical structures. Be houses taller than 15 meters, bridges, stadiums, dams, or very critical structures where failure consequences would be extremely severe. The consequence class 2 and 3 influence the KFI factor. KFI 1.0. For consequence class 2 is what we normally use. If the consequence class 3 is used, we have in Denmark an increased safety factor by a factor 1.1. As I said, the most common in Denmark is CC2, leading to normal safety coefficients. Safety factors in Denmark, very typical for loads, we use gamma Q 1.5. The friction angle, we use gamma phi. This is 1.2 multiplied by KFI. And if you remember that KFI was normally 1.0, then typically the friction angle has a safety factor of 1.2. Same for effective cohesion, or C prime. The safety factor gamma C prime is 1.2 multiplied by KFI. If we used undrained shear strength gamma CU, we have a safety factor of 1.8 multiplied by KFI. All these values you will find in annex to the Danish national annex to the Eurocode 7. The friction angle, don't forget how we use the safety factor on the friction angle. It is not on the angle itself, but it is the tangent value we divide with the safety factor. Just to make sure you understand the use of safety factors in Denmark, we now have an example. We are assuming consequence class 2, giving us a KFI factor of 1.0, meaning that we are not increasing the safety factors by 10%. We have so-called normal safety factors. A quick run through of the characteristic values. We have a surface load of 20 kilonewton per square meter. Then we have density of soil, 21 kilonewton per cubic meter. We have an effective weight of 11 kilonewton per square meter. We have long-term state parameters, C effective friction angle 30 degrees, and then C prime, the effective cohesion of either 0 or 10 kilonewton per square meter. For use in the short-term state analysis, we have a friction angle of 0 and an undrained shear strength of 100 kilonewton per square meter. So for design purposes, we would need to change the characteristic values into design values. For the surface load, we increase the load by the safety factor, meaning that we have the 20 kilonewton per square meter multiplied by 1.5, giving us a design load of 30 kilonewton per square meter. The friction angle, we take the tangent value of the characteristic friction angle, and then we divide it by gamma phi, which is 1.2, and then we take the arcus tangens value of that figure, giving us a design friction angle of 25.7 degrees. The effective cohesion, the C prime, we get that by reducing the characteristic value with the safety factor for C prime, which is 1.2. So instead of having a value of 10, we have now a design C prime value of 8.33. In a similar way, we reduce the characteristic undrained shear strength with a safety factor 1.8, giving us a design value of undrained shear strength of, this was supposed to be C, of 100 divided by 1.8 equals 55.7 kilonewton per square meters. So as you see, the use of safety factor in geotechnical engineering, we increase the load and then we decrease the strength parameters of the soil. And this is then the method that we use to determine the earth pressure, which is a very big part of the content of the 4th semester here. That's all for this presentation. I hope you enjoyed it and that you're now ready to start the course GSW2.